Astronomers believe that all the matter in the universe was once contained in one place, bound by mysterious forces of incredible strength. Some of this matter formed our world, where its appearance is constantly changing. But what is matter? And what holds it together? The answers may lie deep inside atoms where tiny particles called quarks exist. Many scientists believe that quarks hold the key to the secrets of our universe. Throughout the ages, we've been breaking the universe into smaller and smaller bits, looking for the ultimate building blocks of matter. The classic picture of the atom shows electrons in orbit around a nucleus. But today, the picture has become more refined. We now know that the protons and neutrons that make up the nucleus are themselves like miniature atoms made of even smaller particles called quarks. Quarks were first detected in 1968. From the beginning, researchers were puzzled by their behavior. Quarks are particles that have a special force that binds them together and doesn't let them escape. This force is called the strong force. But what is this mysterious strong force, which is unlike any the world has ever seen? To find out, scientists need an instrument that allows them to measure and study quarks with great precision. That instrument is the Continuous Electron Beam Accelerator. And its home is the Thomas Jefferson National Accelerator Facility in Newport News, Virginia. Jefferson Lab is a nuclear physics research facility funded by the U.S. Department of Energy. More than 650 people work at Jefferson Lab. And an additional 1,300 scientists and students from all over the world use the lab to conduct research that can't be done anywhere else. The ultimate goal of Jefferson Lab is to answer some of the most challenging questions ever asked. What is our universe made of? How does it stay together? In the past, scientists answered these questions by building ever more powerful light microscopes. These microscopes work by shining light on an object. Light particles, called photons, bounce off the object, are magnified by a lens, and enter our eyes. Light-sensitive cells in our eyes collect the light and send signals to the brain. Atoms pose a challenge because they are very tiny. A single piece of aluminum foil is 250,000 atoms thick, but we can see individual atoms with the help of powerful electron microscopes. Quarks, though, are at least 1,000,000 times smaller than atoms, and conventional microscopes do not work at that scale. To see quarks, you need a microscope powered by an accelerator. Jefferson Lab's Continuous Electron Beam Accelerator Facility is one of the most powerful microscopes in the world. At Jefferson Lab, we use electrons instead of photons to look into the nucleus. The accelerator sends electrons into the nucleus, where the electrons scatter off protons, neutrons, and their constituent quarks. Large detector systems record what happens when the electrons bounce off the nucleus. The accelerator's high-tech hardware and electronics stretch through an underground tunnel nearly a mile around. When experiments are being conducted, the accelerator runs continuously 24 hours a day. It's not easy to hit the nucleus of an atom. If the nucleus were as big as your fist, the electrons circulating around it would be more than a mile away. Because atoms are mostly empty space, the accelerator must fire billions of electrons at enormous speed in order for one to hit the nucleus. Jefferson Lab's electron beam begins here in a device called the injector. 3 streams of electrons are merged into a continuous strand the size of a human hair to begin their journey around the racetrack of the accelerator. They'll accelerate from a standing start to nearly the speed of light and travel 5 miles in 30 millionths of a second. The electrons gain energy by surfing on waves of electrical energy. The donut-shaped cavities that contain these waves are made of a special metal called niobium. When currents travel through most metals, the metal offers resistance, but niobium is a superconductor. In conditions of extreme cold, it loses nearly all resistance. Hundreds of these cavities line the straightaways of Jefferson Lab's accelerator oval, chilled inside giant thermos bottles called cryomodules. Chilling the niobium cavities not only allows the accelerator to run continuously, it also allows the accelerator to use far less power than older accelerators. Superconducting technology makes Jefferson Lab's accelerator the most efficient particle accelerator in the world. After 5 laps, the electrons are routed to one of 3 giant experimental halls where the beam smashes into its target. The beam ricochets off the target's nuclei and their protons, neutrons, and quarks. The target chambers are coupled to massive detectors that measure the interaction between the electrons and the quarks. In 2 of the halls, carefully placed spectrometers the size of a house measure particles flying off in specific directions. In the 3rd hall, a giant spherical detector can track particles flying in almost all directions at once. Whenever a particle is detected, an electrical pulse is sent down cables and is recorded by computers. The lab uses powerful computers to scour the vast amounts of data produced by each experiment, looking for patterns in the particles scattered by the electron beam. The research conducted at Jefferson Lab and other national labs has led to the development of technologies that directly benefit society. We partner with industry and university researchers to share scientific discoveries and industrial applications. At Jefferson Lab, we are a world leader in superconducting accelerating structures, liquid helium refrigeration, and high current electron injectors. In fact, Jefferson Lab leads the world in operating experience with superconducting linear accelerators, making us uniquely qualified to design and apply new advances at other laboratories in the U.S. and abroad. Jefferson Lab also operates the world's largest facility for fabricating superconducting radio frequency cavities and has produced about 40% of the cavities worldwide. Our cryogenics group has received numerous awards for improving the efficiency of cryogenic plants at NASA and other Department of Energy facilities. And the lab's patented cryogenic processes have been licensed to a commercial vendor for use in existing and future plants. A spin-off of the technology at Jefferson Lab is a unique free electron laser. Our FEL is the most powerful, tunable laser in the world. This extraordinary laser was made possible by using the same superconducting technology that powers the Jefferson Lab electron accelerator. The power and tunability of our free electron laser has opened the door to new industrial processes and research. For instance, scientists have explored new ways to modify the surface of metals to make them stronger and more resistant to corrosion. A new laser treatment for fat cells may help prevent breakouts of severe acne in young adults. And laser-based micromachining is allowing researchers to build tiny, cost-effective satellites for future space applications. Jefferson Lab also has made breakthroughs in medical imaging. The same technology used by detectors in the lab's experimental halls has been developed with the help of lab scientists into compact medical imaging units. A Jefferson Lab-developed breast imaging unit used in conjunction with mammography has dramatically improved the detection of breast cancer and is saving lives. Jefferson Lab detector and imaging scientists continue to develop other specialized units for biomedical research and drug testing, as well as other dedicated cancer imagers. Jefferson Lab also applies its knowledge to educating the next generation of scientists and engineers. Lab employees share their passion for science and exploration through a number of education programs that reach out to students of all ages. Programs designed for science teachers and students in grade school, high school, and college have increased students' knowledge and appreciation of math and science. College students from around the world come to Jefferson Lab to gain hands-on experience as they work toward advanced degrees. Each year, about 1/3 of all nuclear physics PhDs awarded in the United States are earned by students who conducted their research at Jefferson Lab. Clearly, the research at Jefferson Lab has profound implications for our future. Science has an enormous impact on our society. It fuels economic growth and improves our lives. By studying the very small, we can learn about the very large, our universe and all that it contains. To expand the opportunity for discovery, Jefferson Lab is upgrading its facility at a cost of about $300 million. The project will see the lab double the energy of its electron beam from 6 billion electron volts to 12 billion electron volts, construct a new experimental hall, and upgrade the 3 existing experimental halls. The 12 GeV upgrade will allow Jefferson Lab to employ new methods for studying the basic properties of the building blocks of the universe, how they are formed, how they interact, and the forces that mediate these interactions. Through experiments aimed at revealing these and other secrets of matter, physicists will use the upgraded accelerator to contribute to Jefferson Lab's mission of expanding our knowledge of nuclear and particle physics well beyond its current level. Construction is underway and scheduled to be completed in 2015. Throughout the 20th century, the electron and its applications dominated technology and revolutionized human society. Perhaps the 21st century will be dominated by the quark and the remarkable forces that forge and shape the atomic nucleus. If so, Jefferson Lab will be in the forefront of that effort.